So we should be ready to go now. So hello, welcome to my talk. Welcome to CppCon 2021, even though you've probably been there for the whole week. If you're lucky as I have been, you've seen and heard some wonderful talks. I hope this one will make you smile. It's called Evolving an Ice Trick, and I'm hoping that, yes, cool, that you can see something. So my name is there, and so are my email addresses. You can use either one to contact me should you have any questions, comments, or threats to formulate. I'm a professor at Université de Sherbrooke in Quebec and at Collège Nelgro. Both have let me be here for the week, like they often do, and they're very cool about that. If you've never heard about me, I have a number of kids, but they're not at home right now, so we should be okay with this. There's a number of animals at my house, so there might be noises because I'm doing this from my house. I have to do the conference remotely this year. I miss you all in person. I prefer to be there normally, of course. In the past, I used to do work related to industrial research and military flight simulators, which influences a bit my thinking and the kind of classes I give. I've been teaching for 23 years so far at both schools, and I incidentally happen to be a member of the C++ Standards Committee, not the most visible one, but I'm there. And I enjoy it, and I do my best to contribute to the language in whatever way I can. I mostly work with game programmers these days, so that might be what I've been most associated with in recent years. So there. This talk is meant as a feel-good talk, to be honest. It starts with we have a problem, but still it starts as a feel-good talk. I've seen some profound talks, a number of them this week, exploring a number of deep problems and fun. In my case, it's a very simple problem, but it's one that shows us, if we look at it through an historical perspective, how beautiful the language has gotten over the years. So that's why it's a feel-good talk. Going through history, we'll be able to take a look at what we had to do to get the job done and what we can do today, which is the goal. So this is the situation. To put you in context, a few years back, when the kids needed dental work, I took a side contract to make some money. And in that contract, I had to work with very old tools. To be honest, I had to work with tools that weren't in use anymore when I started teaching 23 years ago. Then for a company that did real-time systems and certified binaries. So they were really reluctant to change the tools that they were using because there was so much money involved. So since I had to go back to barely C++ 98, I had to get my bag of tricks back again and enjoy the language as it used to be. Given that I work on the language that will be tomorrow these days, it was a bit of a different experience. So the problem that we faced there, that was a small speck in a big problem, of course. Comparing two values. Now, I just came out of Walter Brown's talk, where Walter was exploring in detail how you can check if two values are out of order with respect to one another. I'm just going to check whether they're equal. It's much simpler. Walter is a deep thinker. So something like this with integers, I guess, kind of makes sense. I mean, you have two ints, you compare them with equal, you expect them to be pretty much okay. And then when you're writing something with floating point numbers, you can write something like that. Now I know, before someone complains, I know this is not right. Don't worry about it, that's not the point. But the idea here in this case is that we have different algorithms for different types, different families of types at the very least. So I know that A minus B can overflow. That's not the point of this part of the talk, at least. So there, when you have ints, when you have floats, this is an easy problem to solve. Of course, it's like first year student stuff. If you want to write it in a generic manner, it's more interesting though. So if you start with this thing and you want your functions to have more homogeneous names, well, you can give them the same name. In this case, I went for a general case. Are two ints close enough? Yes, if they're equal. Are two floats close enough? Well, if they're within some kind of tolerance threshold to what I can tolerate, something like that. It's like observing a value and seeing if it's close enough to your needs. Let's put it this way. If you want to just turn them into templates, it might not do what you want, because of course, if I write it the way I write it on this slide right now, you end up with ambiguous calls. Should you try to call this function with two ints? or two floats, or two doubles, or what have you, because how can you distinguish between the two signatures? Well, that's self-evident for the kind of people we have at CppCon, of course. So, writing a generic close enough function that performs sensible comparisons for a given arithmetic type. That's the goal. Now, remember, when I played with this trick that I've been using for a long while, I was doing this work for a company that used very, very old tools. So they were kind of surprised that we could approach this from a generic perspective. We tend to forget, since we're doing very complicated stuff sometimes, that these little things that make our life better, well, they're not always self-evident to people who are working on other problems. And they're bright people, but they're solving other stuff. So having a generic close enough function that I give to which I give two values of, let's say for the moment, the same type, and tells me whether they are close enough or not, to the people I worked with, it seemed like a big problem. Of course, it was a smaller subset of their real problems. So in itself, it's not hard if you think of it. Before we go into C++, it's a problem that's hard to solve in many other languages if you think of it. I could have taken Java, C# or a number of others. I'm playing with C# these days at school for some of the classes that we have to give. It turns out that writing a proper solution to this in C#, it has costs. It's not easy. And I'm not blaming C#, the general model of those languages that makes it complicated. So in C#, they rely on interfaces, I-equatables, where you define where the rules for a given T to be equal to another T are. But there's costs to that because you're going through interfaces, so you're paying something. So if you take the non-generic example, it kind of looks like this in C#. It's not bad code. You have a value in your integral. Let's say you want to compare integrals. And because of the basic model that they had when they started the language with, everyone inherits from a base class named object somewhere up there. And object as a polymorphic equals function, member function, method in their case, that takes an object as argument. And then you have to check if the object is of the right type for you. So there's some kind of cast to do, the is that you see there. And then after that, is will take care in this case of null and not null, which is a good thing. And then you have to downcast the object to something else to be the actual comparison. So it works. But there's costs there. So you have to do some kind of introspection and stuff. It's costly. If you implement the I-equatable interface that they use with generic code, you end up with, before I go further, C# is not nice to you. If you want to implement equals, you're going to have to implement different than, and you're going to have to implement get code if you want to get the warnings out of the way. It's kind of involved to do comparison in that language. Still. And yeah, we have an indirection and downcast, as I was saying. Now, if you look at this with the I-equatable thing, you can split into two functions. So you probably should write the equals object function because the type system kind of expects you to do so. It's kind of weird if you write equal, but not the equals function. You end up with the function at the bottom there, the one that takes an object as argument that makes sure that the object is integral and then names it n, kind of like the syntax that Herb was using in his keynote this week, and then takes that n and calls the equals on integral, which is the one that's in the middle on the slide, which has to compare with null because if you call it with null, it's going to crash otherwise, and then compare value with value. This kind of works nicely in generic code because C# code will expect you to implement I-equatable and will call kind of directly your function there. What's annoying, of course, is that you're playing with references, so you're incurring checks to null, and you're incurring indirection costs too. So it's more costly than I would, than C++ programmers would be comfortable with, probably. Still, you can write a generic close enough function like this in C# if you have two T's, and you put the constraint that T is I-equatable, kind of concept-ish, let's put it this way, although it's really not concepts in this case. And then given that you've guaranteed, statically speaking, that your type T implements the interface, you can call equals on it. But think about it. Now you have an intrusive technique, you impose an interface on people, You have to check for null, even though it's probably not necessary all the time. There are new mechanisms to make that less important. And you have to do indirect calls to do the job. So it's not something C++ programmers are used to doing. And if I wanted to do something like close enough T and U, say, it would be very messy in C#. I'm not sure I could write it properly with the language that they have today, which is not to say it's a bad language, just weird. So C++ programmers, we tend to go for non-intrusive solutions. We prefer not to impose interfaces on people, and we don't want to make everyone pay overhead costs for comparisons. Otherwise, well, they will just do equals by hand, or write the code by hand, or use macros, or what have you. Thus, as I said, I'm going to go back in time, 1998. Make the code work. It's all code that works. There's got both links all over the place, you'll see. And gradually make new features come in and make the solution better. It ends up being quite nice in the end, which is why the talk is named Evolving in Ice Strip. It worked. Today it works better. So back in time. If you're old enough to remember this time, welcome home. I know a number of our attendees this week have not necessarily played with this kind of C++. You see, it's still kind of neat for what we can do. So C++ is backward compatible quite a bit. So the code I'm going to write there still works today. You'll be able to check it on Gunbolt if you want. So I'm going to use stack dispatching for this first example. The trick is, I'm going to write functions of different signatures for each of my algorithms. So my close enough with integrals would have a different signature than my close enough for floating points. I'm going to make sure that these functions, I'm going to hope that people don't call these functions directly, because that's not the point. The point is for them to do the legwork, the work, and for some other function to call the right one according to the circumstances and the types involved. The tag types will be instances of empty types, so objects that have essentially no weight or close to no weight, essentially free. With these tag types, I'm going to have my different signatures, and I'm going to be able to make the inliner do the work for me. And then I'm going to add that function that people will actually call, which takes 2 arguments as expected, not 3 with the added tag type, and forward the call properly, not in the forwarding sense that we have today, to make sure that the proper algorithm to do the job will get called at the proper moment. And it just turns out that with templates and stuff, optimizers are quite good, and they were quite good even back then. So these are my tag types in this case. I'm going to use exact for those who have an exact-ish representation, integers mostly for my case, and floating for those few that have a floating point representation. Now remember, we're using old code pre-C++11, so I have to do a few things myself. The algorithms that do the job, they're the same functions we saw before. So close enough with integers, say integers-ish, have the exact tag type, and close enough for the floating points have the floating tag type. So that's what you see in the boldface words on screen right now. Sorry for the noise. So taking this as is, you might notice that I changed my constant in the floating point close enough to a static cast to T of my threshold to make sure that I do same type comparison in this case. So these functions, as I said, are not meant to be called directly, they're meant to do the job. The arguments have no names, so it's deliberate. It's to avoid warnings such as unused variables. These days, we could give them names if we're so inclined and put maybe unused on them or something. They're meant to give different signatures. That's what they're there for. As I said, I have a type literal in this case. It's going to make for better code in the end. Now, since we're in 1998, we don't have the traits that we have today, so we have to write them by hand. We don't need much. We don't need the whole set of traits that we use today. But you do have some questions to ask ourselves. Like one of them is, what's a floating point number? When you have a T, is it a floating point number, yes or no? It's not as hard to do. We take it for granted these days. We could write a close enough for each and every type of floating point number. There's only 3. For the others, for the integrals, it would be a bit painful. So if we take this technique now, so we have this basic isFloating trait written by hand that uses old style enums for the values. So this one is false by default. So I'm saying, in general, most types are not floating points, see? But there's these 3 at the bottom: float, double, long double. For these, the value will be true. So I have a home main type trait to tell me if something is a floating point or not. It's extensible should someone want to add floating point types like float 16 to the list, should we ever get there. Kind of works. I deliberately, it's written in the comment there, use the con value convention that has become the standard over time, just to save time in this case. So there, I have my own trait. I could write it this way too. This is even nicer, so I'm going to stick to that. It's the technique that the books people were using. I think it's Dave Abrahams, I'm not sure. I saw he was here this week, so maybe he will correct me if that wasn't him. So a very simplified true type and false type. There's more to that in practice. It's more clever than this. But there, false type to represent the concept of no, and true type to represent the concept of yes. And I just make my isFloating general case be a false type and the other ones be true type, which gives me less code to write and makes it homogeneous kind of by default. It gives you the same results really. Now I need a compile time if-ish of sorts to pick between the 2 types that I'm going to use. So am I going to pick the exact overload or the floating overload? We don't want to use an if statement for that. That would involve branching at runtime. People wouldn't call the function. We need that thing to be resolved at compile time. So we don't have type trace. What do? We write ourselves one. So I wrote this static if-else-ish kind of thing there that takes a Boolean in 2 types. If the Boolean is true, I pick the first type, the one that represents the true type. It's not the true type in the sense that I had in the previous slide. The type to pick if the constant is true. And in the second case, if it's false, I'm going to pick the second type. So this pattern lets me pick between 2 types, depending on a constant time or a compile time condition. There. Given that we have this, now we can do this kind of lifting that we have to do with the function that people are going to call with 2 arguments. So a close enough thing there that takes 2 t's and relays the close enough to the call close enough that takes 3 arguments. Now the boldface stuff in the middle, as you probably know if you're at CppCon, lets me pick between floating and exact based on the value of the isFloating t con value condition. If it's a floating point, I'm picking floating. If it's a non-floating point, I pick exact. It's an arbitrary choice, of course. The type from within that thing is a dependent type because it's a generic thing of a generic thing of a generic thing or something. So I need to put type name at the beginning to say, no, I swear it's a type, believe me. I know it doesn't look like it from this place, from this perspective. You have to believe me in this case. And then I cheated. I used braces at the end out of reflex. I just noticed it. I could have put a pair of parentheses back then and made some work to make it work. But then I'm going, if you look at this one, I'm instantiating, making an object of either floating or exact, depending on the constant that I had as argument, also depending on whether it's a floating point or not. It works. It's awesome. Now you should have seen the people I was working with saying, you can actually do that. That's crazy. Yeah, but sorry for the song. It works. It works fine. I mean, it does the job. It resolves to the right things for you. And I know my algorithm is a bit ordinary to compare the 2 floating point numbers, but put the actual algorithm there is going to be fine because we've seen from Kevin in his talk earlier this week and a few others that this kind of comparison is a bit dangerous in practice. You don't want your plane to fall down if you use something like that. So they were happy. They asked me if they could keep it. So of course, there's nothing magic there. It's all like common practice. But if you're not familiar with C++, it's surprising. You show that to a programmer that does Java code, it's kind of astonishing to me. You can do that. But this slide is the entire code indented as slideware to make it kind of fit. So the braces are all on the same lines, almost, I think. It's kind of a mouthful. There's a lot of code to write to make it work. Of course, most of that code is reusable for other stuff. Still, the only thing missing there is the test driver, the main code. But yeah, it works. It works. You can try to get both link if you feel like it. So it's a lot of effort if you only want to compare floats and ints, but it's cool to know that you have a generic solution. It works with very old compilers. Now, it's not free, as you can see. There's some effort and sweat involved. And the only function that we really care for is the one at the bottom there. And that's the one that people want to call. We did all that work for that single liner there. So it was just a mean to pick between two algorithms to solve the same problem. Lots of sweat and blood and tears. Well, not tears, it's fun to write. But yeah, when I started teaching, we had to do things like that sometimes. C++11 was awesome. It still is awesome today. I still love it. The number of things it has changed in my life, and I hope in yours, has been amazing. Just the first time that I wrote include thread, I was so happy. So inspired by community practice and by what the Boost people were doing and people like me on their own side were doing, C++11 has introduced type traits. Some of them we could write ourselves, some of them we could not because they require some knowledge that the compiler as of the source code likes. Something like is polymorphic. So things such as compile time type selection, my static if else, now it's named conditional. True type and false type, they're standardized. Is T a floating point type? We have a trait for that now. So all of this stuff is standardized. So if we go back to the slides there, almost everything there has been standardized except for the actual algorithm with the tag dispatching stuff. So yeah. So that entire slide melts to not much. The boldface include there, that includes type traits, does much of the brunt work. And the rest is my basic algorithm there with close enough with T's exact and close enough with T's floating. I changed my code at the bottom for a call to type name std conditional and std colon is floating point value because these are the names of the actual type traits. That's quite an upgrade. I mean, it's less than half of the code to write, but conceptually speaking, it's the same code. I mean, I did write 3 functions where I, in practice, only wanted the one at the bottom that people will call in practice. But the point of that function is to relay at essentially no cost the work to the right function. And since function signatures, they're known at compile time, well, we can map efficiently to the right one without having to branch or anything. So the plain people liked it. Now, we're in 11, there's other things than just type traits. You can check the code, of course it works. There's this new thing called CppCon that I heard some people talk about this week. If you haven't seen Jason Turner's talk, it was incredibly good. Please do so. We've had some very good talks this week. Ben Dean's talk was good. There were a number of good talks. So this CppCon thing that lets us resolve things at compile time seems to be a good fit for this tool because when we're comparing 2 integers, if I know my 2 integers at compile time, why pay for it? You know? So the trick is we want this thing to be compile time if A, the arguments are known at compile time, and of course if the context demands it. Now that's an understated advantage of CppCon. So people want consteval sometimes, oh, why is compile time? But the point of CppCon is you can debug it, which is pretty cool. Because before CppCon, to get the same kind of effect, we had to do TMP, template metaprogramming, and that was something to debug, let's put it this way. I remember having spent a few afternoons over coffee looking at very strange code and trying to find ways to identify where the bugs were, because I couldn't trace through it. So it appears to be a good fit with what I'm doing right now. The first one that we can check, that's quite easy. As I said, I think it's pretty much self-evident that if I have 2 integers and compare them with equal, And I know my integer at compile time, there's no real reason not to let it be possible. So that seems reasonable right now. If I leave it this way, though, I'm not really good, because the function that's going to be called is not this one. This one is an indirect call. The real call is below, but it's a start. No? If I want to make the call below the one that people actually call const_expr, the building blocks have to be in place. And this one is kind of easy. This one is trickier, because if you look at it, sometimes I show this to students and say, well, just put const_expr. No, it won't work. It won't work because we have this absolute value function there that comes from C. And C doesn't know const_expr much, even today. We're trying to add const_expr to C math these days. There's work involved because there's functions in there that do with error no. So, but this one, if we remove std call abs, there's no real reason not to do this const_expr. But we can write our own, can't we? We can. So if we put that absolute function that I just added there above my close enough floating version, that's naive. It's probably not as efficient as std call abs, but for my purpose, it's enough. Well, I can make my close enough function const_expr, which I just did now. So it's pretty neat. The static cast to t there is a compile time thing because it's a constant value. No problem with this. So since we have two const_expr close enough functions that implement the algorithms at this point, the dispatching function can be made const_expr too, because what does it do? It evaluates the compile time constant, takes between two empty classes, really, based on this compile time constant, instantiates an empty class and calls the function with it. So everything in there can be the compile time, essentially. That's awesome. So we can now test this thing with static assert. This is pretty neat. In fact, as an underlying foundation for other stuff, so far we can write classes that use arbitrary values in there and see if they're kind of equal with operator equal by calling close enough in there. Supposing that you have a close enough or floating point that suits your needs. And you can write quite parable code at compile time. I mean, I've written entire classes that just do the job and are runable with this. Still, lots of code for our needs, but with this, it's pretty satisfying. Okay, just you compile this with static assert and there's no code, essentially, it's beautiful. Okay, so it's a very big step ahead. const_expr changes everything. I mean, it keeps changing the language even today, that thing. So I think it's Gabriel's Reis's idea. It's a beautiful idea. Maybe Bjorn is too. So now we have three algorithms. People who look at this say, well, it's kind of wasteful. You have three functions, but two algorithms. There's kind of a mismatch there. It lacks elegance. You might see that the title of the slide is adding enable if. Short story, if you may. I was on a panel with Chuck Allison, Bjarne, and a guy named Andrew Lumsdaine a few years back at CppCon, and we're talking about education. And Chuck invented bitset and vector bool. He didn't name it that way, though. Bjarne invented so many things, it's hard to keep track. And there was this guy, I didn't know him, but I knew he had a big pedigree. It was important. A number of his students went to the standard at some point. He said, I did Bootstrap, and I'm guilty for bringing this enable if to the fore. That's the words he used. Guilty. I said, hey, whoa, he invented enable if. That's awesome. So Andrew, if you didn't see his talk on graphs this week, great job. It was a really good talk too. I really liked it. So enable if you haven't played with this, it's kind of weird. It's strange, you know. The thing is, you're kind of telling the compiler, well, you have these functions or these types or whatever. There's a few of them I don't want you to see, that I don't want you to look at. If you look at this slide, I have two functions. It's slideware, so the disposition is a bit weird, and the bold-faced lines are pretty strange if you're not used to enable if. Of course, if you are, it's easy for you. So I'm saying with the first one, well, that function should only be considered if t is not a floating point, that there's that exclamation mark at the middle there. And it will return bool in that case. That's the comma bool that you see towards the end. And the second one says this function should only be considered if it is a floating point type. It should return bool. What happens is that the compiler looks at both of them, looks at t. And t only falls within one of these two categories. It's either a floating point or it's not. And the one for whose the condition doesn't match, well, it's removed by fine. The type there doesn't exist. Fine makes it go away, and you're left with only one overload possible. So you don't have to have this dispatcher function. But it's kind of a strange trick. And there's this huge type name called colon type thing to write that makes it a bit heavy. So yeah, so the first one exists only if t is not a floating point. The second one exists if only if t is a floating point. There's no not there, so they're mutually exclusive. And what happens is that the one that doesn't fit has no colon type at the end, so it's finite away because it doesn't work. It's badly formed or something. So you end up with something kind of cool. There's only one function for each type t there, but it's very hard to explain. So you put that in your slides or in your code with people who are not used to C++ idioms, and you're in for a nice session of coffee drinking with them. But it works. It works. And there's less code on the slide. As you can see, there's only 3 functions now. There's the absolute thing that I had to write to make my stuff const expr. There's the 2 functions that do the actual work. There's no relaying function. Now the type traits are the type traits. Beautiful. Let's go. Now comes C++14. I've heard a friend of mine say on the core working group that, well, C++11 was a big change, but C++14 just saves you some typing, which isn't exactly true. You know, we've got generic lambdas in there, and const expr does more than it used to do. So it's not as matter as people make it look like sometimes. Still, for me, for this example, what's interesting is the underscore t convention. Some people find it ugly, I know, but it is useful. So by adding aliases for underscore t for the traits that end with colon type, we actually simplify generic code quite a bit. Look at it. So if you take the old remove const stuff, simplified version, of course, I have the 2 patterns above, no boldface. The one that says for a type t, remove const of t is t. And for a type t, remove const of const t is t. Essentially the gist of it. So at the bottom, there's the new stuff. Remove const t of t. It's equivalent to the type name, blah, 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 colon type, which simplifies writing code quite a bit. And what C++14 brought was the standardization of that convention. So the traits that end with types have this underscore t at the end. Seems minor, but when you do nested traits, it's awesome. So the one above is replaced, well, can be replaced if you're so inclined by the one below. Now remember that huge line with enable if. We start with this, type name, std concon, enable if, the condition, the type, concon type in this case, and you end up with this. It's quite shorter, back, forth. It's kind of cool. I mean, I almost removed 15 characters from my line, and that propagates throughout the code. So this minor upgrade makes my programmer's life easier. I like it. And sometimes the small things make a big difference in your day. If you forget the type name somewhere and you have a weird error you're having a hard time understanding, this kind of stuff can save you time. Yeah, and headaches and stuff. So you can still try it if you're unconvinced. We also have generic variables. That's minor in this case, but it's still fun. Generic variables come with C++14 as far as I know. And the canonical example of that is the pi there that you see in the middle. Pi of t is a cast to t of this big, complicated pi value. And you can have pi of float, pi of long double, and pi of int if you're really, really, really strange and you're really looking for trouble. But yeah, that works. So we can do this with our threshold, make it look a bit nicer. So we had a static cast to t of a threshold. With this, we can have a constructor variable. The name threshold is not a good name in this case. I know it's slideware again. So the boldface, as you can see, it's meant to bring the intent to the code instead of, I could have made it a local constructor variable to my function to make it less polluting. But let's put it this way for the moment. So the code, I think, probably expresses better the idea with this than with the actual cast in the code. So these are small things to do indeed, but they do make our lives better. Okay. If you want to play with it. Come 17. Some people don't like 17, and I understand why. We were expecting big features, and many of them didn't make it. But there's those small things again, and sometimes not so small things that have made a difference in our lives. Remember where we started from. We're getting to somewhere very cool now. So there's this V suffix that we're using for values now. So traits with types and with T, underscore T, traits with values and with underscore V, it's a convention. It makes a smaller difference because we don't have the type name dance to do. But still, we have this before there with the boldface. And this is the after. It's still shorter. So if I went 2 steps behind to add the type name and the colon type to that, I haven't halved my line length there, but close to it. So it is an upgrade. To check, of course. But bigger than that, we have if const expert. So if we look back at one slide there, enable if, it's not everyone's cup of tea. Some people find that hard to grasp. That's totally fine. It's a weird beast that has been very useful. I mean, I'm glad we've had it. But we still have it sometimes. But no, the idea of having an if and saying if my type is a floating point type, I shall do this. Otherwise, I shall do this other thing. It comes naturally to people. In C++, we don't want to pay the cost of the branch. But if const expert has no cost, see, at least not in that sense, because only the if branch exists if the condition is true, and only the else branch exists if the condition is false. So there's no branching, it's a no-cost thing. As long as, of course, you have a compile time constant as your condition, which is our case. Well, that makes one happy. There was resistance to that when we voted that in. We were afraid that it would slow down the advent of concepts. But both are useful. And if const expert has been useful for the time we didn't have concept in the meantime, and we're all happy to have concepts anyway. Concepts are really, really cool. So we go to that. Now we've gone from 3 functions in C++98 to 2 functions with enable if, but a lot of noise with C++11, to less noise with C++14, to 1 function in C++17. The underscore V thing is there, and I have something that looks natural. I think the big difference is that's much, much easier to teach and understand for many people. Or the programmers, the C++ programmers who aren't used to the intricacies of template programming. So we have this thing that looks like an if, behaves like an if to the onlooker, but is actually a code-generating device. It generates one of the 2 branches, not the other. It's easily debuggable. You just step through it, works fine. And it's a no-cost thing. So yeah. When I show this to people, after I've been shown enable if myself, say, whew, that I understand. You end up with the same effect in practice, but that's understandable. Yeah. It has a lot of other upsides too that I won't get into because that's not the point of this talk. So if we recap, just because we've gone through some time, there's been some gap between 98 and 17. It's been 20 years. We had this at first. Quite a lot of effort. But there's practices developed over time that work, that give us ideas, that grew. And I'm only skimming through it because things like true type and false type, they're more complex than what I made them look to be. They're more interesting. And then I go to this with 11. With noise, but 2 functions, well, 3 if I count the absolute thing there because I want context expert. Type traits has been a boon for this kind of code. To 14. Back, forth. The amount of noise is much smaller. There's still noise, of course. To 17. Just 1 function. More understandable. People probably grasp the intent just by looking at the code and say, okay, kind of makes sense. That's what I would have written myself under such circumstances had I known that the feature existed. I can get why the constant, why the condition has to be compile time. So I get it. That's cool. But C++20 is a beautiful thing. Now I'm working on a C++20 class these days. It's huge. It's huge. Normally I give 2-day classes. This one is probably going to be a 3-day class when I end up doing it. It's a big beast. There's a number of interesting things in there. It changes the way we think. It brings a lot to the table, kind of like C++11 did. But for this problem, we don't have to look at everything. We can be more focused. So we have this if context expert, which does the job. And there are some things that are done very well with if context expert. It works, it's cool. Still, we can make it a bit nicer with C++20. It's kind of worth doing it. Among other things, the solution that we had with if context expert wasn't necessarily suited to comparing integrals of different types. It was T and T, or floating points of different types. So if I wanted to see if a float and a double were close enough, it would have been a bit more work than I would have liked. I would have had to find the common type between them, blah, blah, blah. With concepts, sorry for my noisy throat. With concepts, we add beauty. With beauty. So this is one way to do this if you haven't played with concepts, but from what I could see this week, many of you had, which makes me so happy, you have no idea. So including concepts to get the standard concepts with me, because integral is a standard concept. It's kind of like a trait, but a bit nicer. Well, there are things you can do with traits more, but still. And the floating point concept that I have there. So this version of the code, if you look at the first close enough in the middle of the screen, says, well, if you have a t, but I require that t is integral, close enough tt expresses like this. Now, if you have a t, but I require that t is a floating point, then you have the second one. I just gained something because it's not whether it's a floating point or not. I'm more precise. I'm requesting that the first one goes with integrals. And the second one goes with floating points. Works, of course. So the first one, the one that I had before, would have allowed me to compare other stuff than integrals in the integral case. Would have worked with strings, with well, I feel like complexes or rationals, or tuples, whatever. So this one has the nice upside that if that's what I want to convey, at least, that it is restricted to integrals. So if I put something else, well, that's not the right algorithm. Of course, I could add overloads should I be so inclined. And since I only have one constraint, I can, of course, apply it in the place of class or type name and just restrict my type T there. Now, this version still requires both arguments to be of the same type. So in the case of integrals, it's 2 shorts. So there are 2 ints, but not an int and a short. That's what is being expressed by the constraint there. For some integral t, I want t and t. And if that's what I want, that's fine. Same thing with the floating points below. So if that's what I want, still it's fine. Note that the threshold t at the bottom is easy to write because I know what t is the type of both of my floating point arguments. Works. If I'm willing to accept two different kinds of integrals or two different kinds of floating points. I can even make it simpler. So the first version doesn't even look like a template anymore. Now that's beautiful, at least to me. One of the stated goals of concepts was to make generic programming normal programming, which is what we do today. I'm passing two integrals, integral auto A, integral auto B. They don't have to be of the same type. It could be a short and an int, say, but they're close enough if the algorithm fits. For my close enough floating point version, I have a bit more work to do because I have to pick the type of my threshold generic variable. In this case, I went for the common type of the type of A and type of B, which allows me to pick something cool. If I have a floating point that's a float and another one that's a double, it's going to pick a double. But that's it. I mean, it doesn't even look like generic code anymore. It's constrained code. It's beautiful, I think. I just added functionality to my code. It's more robust than it used to be. There's less noise on screen, I think. I think it's a net gain. Going back to C++, let's go back a few slides. Going back to what we had with C++ 98. And now going up. It's quite the step. That's what 20 years of design do, I guess. Mind you, concepts were pretty much there before, but we had work to do. So again, if you're not used to concepts, play with them. You're going to enjoy. Make C++ fun. Yeah. So we can make close enough 3L. They're both integrals. It's going to work. It's going to work. It's going to give the right result. You can do it with static assert and stuff. It works fine. Likewise, with a floating point and a double. But the trick is to pick the right type for a threshold to have correct code in this case. We can even, while we're at it, add a constraint to our threshold because threshold of t. So some funny person could have put int there and have a threshold of 0, which wouldn't have been unreasonable, but no, why put that with floating points? So I can constrain my floating point, my generic variable there, my threshold, to make sure it works with any kind of floating point, which makes it fit with the design of close enough. I could have also, of course, put it within the function itself. Yeah. While we're at it, why not? And returning to the very beginning of the slides where I said, well, I won't read too much about that absolute of A minus B, blah, 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 even if it can overflow. It's because it would have made for noisy code. It's a very tricky problem. It's complicated. Walter was facing it earlier today. It's delicate to do right. But we have midpoint in C++20. It's context per. It does the job. People who wrote this thing, hats to you. You just made everyone's life nicer. It's in numeric, so I had to add an include there. So that's why the slide is a bit thicker than it used to be, but still, it's correct. So it's correct, it works, and it's beautiful. Kind of cool. And I can even push it a bit if you feel like it. You want to see if a number of variables are all close enough to, let's say, the first one. Well, you can add fold expressions and compare them together, repeating the thing with the fold over and the AND operator in this case. And yeah, fun stuff. You can static assert on it. So the first one will pass. 3 integrals, no problem. Second one will pass. 3 floating point numbers that are all close enough to the first one, perfect. And the third one won't pass because the first argument is an integer and the constraints aren't respected. I expected all floating points or all integrals. Yeah, it's a mismatch. So if we look back, we've always had an expressive language, really. People complain, but think about it. We could do the job 20 years back with the tools that we had. It took more effort. We could do it. We could do it efficiently back then. Surprisingly efficiently compared to other languages that still cannot do it today. Look at it. Indirections, references, test for null. Something that kind of works, but with intrusive interfaces. Again, you have to be careful that A is not null. It's delicate, it's costly. And I'm not even sure I could write close enough TU properly with the language that C# is today. C# is just an example again. I know that Mads Torgersen C# is working on something that might fit with this model, but it's strange. It uses keywords that exist in ways that are surprising. And I'm curious to see where they're going to go with this. But in C++, we have a generic solution. Just follow the type system in our case. So yeah, we could do it in the past. We can do it better today. There's some beauty in the efficiency that we get. The fact that we have values. The fact that we don't have to check for null. The fact that we can write correct algorithms for families of types. The fact that we can make it general. We could make it work very nicely before, even better today. There's beauty in there. So yes, there's beauty in C++. We complain too much. And that's it. I hope it felt like a feel-good talk. It was meant to be. Thank you there. So I don't know how this is supposed to work because I'm a bit early. There's still 10 minutes if there's people who want to ask questions, chat or something. I don't know how I can discuss with you though. So there's a Q&A queue there. Give me a second. So if I go from the top, Leslie says, which talks about float comparisons? I was at Walter Brown's talk just before mine. I had to leave a bit before the end, but Walter was studying in detail things like the less than operator and how we should write min max is sorted until and things like that. It was a very interesting talk on how we compare numbers, among other things. And he did discuss comparisons of floating point numbers. So Leslie, if you want to go check that out, it was a good talk. Gabrielle says, "Have you is this inspired from workshops I've given in the past?" Yeah. This is an example I use when I show constexpr, among other things, because I use that to build classes of concrete types that are roamable, and it surprises people to see that we can just go along and you end up with no code at all, and you can verify that your code is correct with static asserts. It kind of works. Could I have used declaration type over type name on slide 47? So let's go back to slide 47 in a second. I'll be back. Slide 47. There. I'm just going to make sure that I'm reading the right thing. Give me a second. Declaration type over type name. And no, the point in this case is to see if your T is a floating point type. So if I'm reading the same slide as you are, what you want to infer on that one is whether the trait fits your needs. So declaration type, I'm not sure would be a good fit for this one. Now, if I'm not reading your question properly, you can write to me. I'll try to answer you properly. Okay. Could you change the custom assoc function to a lambda for close enough? Yeah, absolutely. But for Chris, who wrote that one, in C++ 11, I would not have it constexpr. So C++ 17 is not a problem. It would totally work indeed. Jan, the gray stuff, I hope is gone now. It's perfect. The average of two, so if I misused midpoint, someone says I misused midpoint, thank you, I'm going to check it out. Thanks. I put that just before I talk earlier today because I didn't want to go there. So Jan, well, the gray spot, Jan, that I just used is the Zoom window that lets me see your questions because I only have one screen. I'm sorry. So Kevin, if I misconstrued the midpoint thing, I'm going to check it out. Thank you. It's quite possible since I put it late, maybe I made a mistake there. So Luca, so you're referring to midpoint 2. Maybe I misused this one. So maybe it's my mistake. I'm going to check it out, okay? Because that I put at the last minute, so that might be my fault. Anything else? I think, except for my midpoint mistake, if I made one, which I'm going to verify, that's what I had in the Q&A window right now. And the chat, I will look later maybe. Okay, anything else, my friends? Okay. So if there's nothing else, I wish you a very nice rest of the day. I'm looking forward to Mr. Sean Perrin's talk later today, and I have another talk before. I'm guessing you folks do too. It's my first experience giving a talk through GatherTown, so I'm going to follow the lead of my friend who will bring me to the right location in the room. If you want to come and chat for a few minutes, feel free to do so. I'd be glad to talk with you. Okay. Thank you all.